ये प्रिंट करना पेन
आपको ना पेन टैप दिखा है
Today we will discuss Eulers theorem. Front, huh?
यूनिट 7 लेक्चर 6 है ना
Okay. Residue लेंगे.
यूनिट 7 लेक्चर 6 है ना
Welcome to the lecture. Today we will discuss Eulers theorem. First I will write down the statement of Eulers theorem. I will write down statement if n greater or equal to 1, if n greater or equal to 1 and GCD of an equals to 1 and GCD of an equals to 1 where a is an integer, GCD of an equals to 1 where a belongs to Z, this means a is an integer, then a power phi of n is congruent to 1 modulo n, is congruent to 1 modulo n. Before giving proof of Euler's theorem, I will give you one example. Okay, for example, 3 raised power, suppose phi of 5 is congruent to 1 mod of 5. We will check whether this is true or not, is congruent to 1 mod of 5. See here. So this is implies 3 raised power phi of 5. Phi is a prime number, so phi of p equal to p minus 1. This means 3 raised power 4 is congruent to 1 mod of 5. Now we will check whether 3 raised power 4 minus 1 is divisible by 5 or not. I will write down here 3 raised power 4 is 3, 3s are 9, 3s are 27, 3s are 81. 81 minus 1 equal to 80. Clearly 5 divides 80. So this is true. Now we will see the proof of Euler's theorem. Before writing the proof of Euler's theorem, we will write down the statement of one lemma which will be useful in proving Euler's theorem. I will write down here before proving the Euler's theorem. Euler's theorem. Before proving Euler's theorem, we state the lemma, which is useful in the proof of Euler's theorem. The lemma is, I will write down the lemma here, if n greater than 1, and GCD of an equals to 1, a is an integer, and GCD of an equals to 1, and if a1, a2, a phi of n, a1, a2, and so on, a phi of n, a phi of n are the positive integers less than n, are the positive integers less than n, and relatively prime to n, and relatively prime to n. That is GCD of AI n equals to 1 and relatively prime to n. Then I will write AA1, AA1, AA2, and so on, AA phi of n, AA phi of n, or congruent modulo n, or congruent modulo n, or congruent modulo n, to a1, a2, a phi of n, a1, a2, and so on, a phi of n, in some order, in some order. Now we will use this lemma to prove the Eulers theorem. Now we will write down the proof of Eulers theorem. Now I will write down proof of Eulers theorem. Proof of Eulers theorem. Okay. I will take first if n equals to 1. See here, if n equals to 1, then what is phi of 1? Then phi of 1 equals to 1. Okay, and as per Euler's theorem, a power phi of n, a power phi of n is 1, a power phi of n is 1. So this is equal to a is congruent to 1 mod of n, n is 1 mod of 1, which is true because 1 divides a minus 1 as 1 divides every number, which is true. Now assume n is greater than 1. Now assume n is greater than 1. Let a1, a2, a phi of n, let a1, a2, and so on, a phi of n, a phi of n be the positive integers less than n and relatively prime to n. Be the positive integers less than n and relatively prime to n, okay. Then are the positive integers less than n and relatively prime to n as GCD of an equals to 1. An equals to 1 because GCD of an equals to 1. Now see here, we take n greater than 1 and let a1, a2, a phi of n be the positive integers less than n and relatively prime to n, because GCD of an equals to 1. Therefore, by above lemma, I will write down here, therefore, by lemma by lemma above, AA1, AA2, I will write down here AA1, AA2, and so on, A phi of n are congruent or congruent or congruent, not necessarily in order of appearance, not necessarily in order of appearance, in order of appearance, not necessarily in order of appearance. To A1, A2, A phi of n, to A1, A2, and so on, A phi of n, A phi of n. Then we will write then AA1 is congruent to A1 dash modulo n, AA2 is congruent to A2 dash modulo n, isn't it? AA1 is congruent to A1 dash modulo n, AA2 is congruent to A2 dash modulo n, and so on. AA phi of n, AA phi of n is congruent to A dash phi of n modulo n, modulo n, where A1 dash, A2 dash, and A phi of n dash are the integers, where I write down here where A1 dash, A2 dash, and so on, A phi of n dash are the integers, A1, A2, and so on, A phi of n, in some order, These are the integers A1, A2, A phi of n in some order, multiplying these phi n congruences. Now multiplying these phi n congruences. This is phi n congruences. Multiplying these phi n congruences, we get now AA1, here we multiply these phi n congruences, AA1, AA2, we get A1, A2, and so on, AA phi of n, okay, AA phi of n is congruent to A1 dash, A2 dash, A phi of n dash modulo n, A1 dash, A2 dash, and so on, A phi n dash modulo n, okay. Now see, and so this is equal to, this is congruent to A1, A2, so on, and so on, A phi of n modulo n, okay, because we are writing here A1 dash, A2 dash, A dash are the integers A1, A2, A phi of n in some order. Okay, we have written A1 dash, A2 dash, A dash phi of n modulo n as A1, A2, A phi of n, and so these are phi n congruent. So here is a1, a2, a phi of n. This means a is phi n times. This means a power phi of n. A power phi of n into a1, a2 and so on, a phi of n. A phi of n is congruent to a1, a2 and so on, a phi of n, modulo n, modulo n. Okay. Now see here, a phi of n is congruent to a1, a2, a phi of n is congruent to a1, a2, a phi of n modulo n. As I will write here as GCD of ith n, as GCD of ain equals to 1, as they are relatively prime for each I. For each I. Here I will write down one more result. Given integers, I will write down one result and name this as star. Given integers, we have integers a, b, c. If we have three integers a, b, c, and GCD of given integers a, b, c and GCD of a into bc equals to 1 if and only if GCD of AB equals to 1, if and only if GCD of AB equals to 1 and GCD of AC equals to 1. GCD of AC equals to 1. So this is one result here. We use this result here as GCD of AIN equals to 1 for each I. Therefore, by I will name this star by star implies by star we have GCD of A1, A2, I will write here A1, A2, sorry, GCD of A1, A2 and so on, A phi of n with n equals to 1 by using this star. As GCD of A into BC equals to 1 if and only if GCD of AB equals to 1 and GCD of AC equals to 1. Okay, now this implies GCD of A1, A2, A phi of n with n equals to 1. Thus what we write, A power phi of n. Thus A power phi of n is congruent to 1 mod of n. 1 mod of n. As we divide by this factor or by cancellation, I will write simply by cancellation. By cancellation. So this proves Eulers' theorem. This proves Eulers' theorem. Now we write here one corollary, and this is Fermat's theorem. Corollary, and we name this as Fermat's theorem. Fermat's theorem. The statement is, if P is a prime, if P is a prime, and P is a prime and P does not divide A. P does not divide A. This means GCD of AP equals to 1. Then A power P minus 1. A power P minus 1 is congruent to 1 mod of P. 1 mod of P. Okay. So this is a corollary of this Euler's theorem known as Hermite statement is, if E is a prime number and P does not divide A, then A power P minus 1 is congruent to 1 mod of P. Okay. Now we take one example based on Eulers' theorem. See here, the questions may be asked like this: find last two digits of number 7 power 81, or find the last two digits in the decimal representation of 7 raised to power 81. I will write down here. Example: find last two digits find last two digits of 7 power 81, or find last two digits in the decimal representation of 7 power 81. So here you note down one point here: for unit digit or last digit, for unit digit or last digit, for unit digit or last digit, use modulo 10. Use modulo 10. For last two digits, use modulo 100. And for three digits, for last three digits, use modulo 1000, and so on. So here we will not use this, we will directly use Euler's theorem. For example, I will tell you one question related to this. First of all, we will take this example: find last two digits of 7 power 81. I will write down its solution. See here, we have to find 7 power 81 modulo 100. Because here we have to find last two digits. If we have to find last digit, then we use modulo 10. If we want to find last three digits, then we use modulo 1000. 7 power 81 modulo 100 equals, this one we have to find. Okay. Now since GCD of 7 into 100, GCD of 7 into 100 equals to 1. Okay. Therefore, then by Euler's theorem, then 7 power a power phi of n, phi of 100 is congruent to 1 mod of 100. 1 mod of 100, because a power phi of n is congruent to 1 mod of 100. Now we find phi of 100 here. Phi of 100. Phi of 100 is equals to 100, 250, 225, 5 into 5. So phi of 100 is pi of 2 power 2 into pi of 5 power 2. So this is equal to 2 power 2 minus 2 into 2 minus 1 is 1. Okay. And 5 power 2 minus 5 power 2 minus 1. So this is equal to 2 to the 4 minus 2 is 2 into 5 5 are 25 minus 5 is 20. So this is equal to 40. So pi of 100 equals to 40. Now we write down here, implies that 7 power 40 is congruent to 1 mod of 100. 1 modulo 100. Now we have to find 7 power 81. Now therefore, now I will write, now 7 power 81 equals to 7 power 40 square is 80, but we need 81 into 7 power 1. Okay. 7 power 40 square into 7. 7 power 81. Okay, so this is equal to this, but this is congruent to 7 power 40 is congruent to 1 modulo 100. So this is congruent to 1 into 7, 7 modulo 100. Okay, so from here we see that, and 7 means 0, 7 here. Therefore last two digits, last two digits of 7 power 81 are 0, 7. Okay, this is a method how we find the last digit, last two digits, last three digits of any number. I will give you one more example. Find the last digit in the decimal representation of, I will write down here. One more example. Find the last two digits. Last two digits in the decimal representation of, in the decimal representation of 3 power 100. Okay, now see here, I will write down its solution. Find the last two digits in the decimal representation of 3 power 100. Simply GCD of 3 into 100 equals to 1. So we will apply Eulers theorem here. Since I will write, simply the given problem is equivalent to find the smallest non-negative integer to which 3 power 100 is congruent to modulo 100, because we are to find last two digits. Now I will write directly the answer of this question, since GCD of 3 into 100 equals to 1. Okay, also we know, we have already proved in the above question, pi of 100 equals to 40. Okay, by Eulers theorem we have, by Eulers theorem we have by Eulers theorem, yes, a power pi of n, a here is 3 and pi of n is 100, a power pi of 100 is congruent to 1 mod of n, n is 100, 1 mod of 100, or 3 power pi of 100 is 40, is congruent to 1 modulo 100, 1 modulo 100. Now we see here, now 3 power 100 equals, as we have to find the last two digits of 3 power 100, but we have find here 3 power 40 is congruent to 1 mod of 100. Now we see 3 power 100 is equal to 3 power 40 square, this is 3 power 80 into 3 power 20 is equal to 3 power 100, but we know 3 power 40 is congruent to 1, 1 square is 1 modulo 100, so this is equal to 3 power 20 modulo 100, modulo 100, because here 3 power 40 I will mention here, because 3 power 40 is congruent to 1 under modulo 100, modulo 100, isn't it? Now we see 3 power 20, I will write down is equal to 3 power 20, I will write down this is equal to 3 power 5 into 4 modulo 100, as 3 power 5 into 4 modulo 100, but 3 power 5 is equal to 3 3s are 9, 9 9s are 81 into 5, I will write down here 81 into 5, this is 5 1s are 5, 5s are 40, 4 not 5, so under modulo 100 it is equal to 5, isn't it? 3 power 5, 3 power 5 into 4. 3 power 5 into 4 modulo 100. 3 power 5. 3 power 5 is 405 and 5 power 4. 625. See here 3 power 40 square into 3 power 20. This is equal to 3 power 20 modulo 100. Now I write 3 power 20 as 3 power 5 into 4 modulo 100. Or this is congruent to, I write, this is congruent to 43. 43 square का whole square. 43 square का whole square under modulo 100. As I will explain you here how this is equals to, sorry, see here 3 power 5. 3 power 5 is 3 3s are 9, 9 9s are 81 into 5. Okay, this is 5 1s are 5, 5 8s are 40. This is 4 not 5 under modulo 5. So this is equal to 43. Square. Sorry, here is 81 into 3 not 5 because we are here doing, here is 3 power 5. 3 power 5 is 3 3s are 9, 3s are 27, 3s are 81 into 3. So this is 3 1s are 3, 3 8s are 24. And under modulo 100 it is equal to 43. So I have written here in place of 3 power 5 I have written 43. 4 in place of 4 I write square का whole square under modulo 100 because 3 power 5 is equal to 43 under modulo 43. Because 3 power 5 equal to 43 under modulo 100 is equal to it 43. So this is equals to, this is congruent to 49 because see here 49 का whole square under modulo 100. How this is equal to 49? See here 43 into 43. So 3 3s are 9, 3 4s are 12 and here 4 3s are 12, 2 1 carry, 4 4s are 16 plus 1 is 17. So this is 9 4 8 1 1849. So under modulo 100 it will remainder will be 49. So here is 49 का square modulo 43 square is congruent to 49 under modulo 100. So this is equal to 49 का square. 49 का square is 49 into 49. We write this as 9 9s are 81, 1 and 8. 9 4s are 36 into 8 is 45. 36 into 8, 36, 44 into here is 36, 90. Okay, 1 0 4 1 1401. 1401 is here. So the last digit is congruent to 01. 1401 under modulo 100 is equal to 01 under modulo 100. So therefore, I will write down here. Therefore, last two digits in 3 power, last two digits in 3 power 100 are 0, 1. So these were some examples based on Eulers theorem. That is all for now. Thank you.